Thank you, Mike. All right, thank you everyone for joining us today for the Texas section webinar. The webinar today is titled Estimating Shrink Swell Movement from Pressure Swell Tests. This is the 7th in our series of monthly webinars for 2018. I would like to thank the branches for hosting viewing sites all across Texas. As the State Association for Civil Engineers, we are happy to provide this service to the engineering community. If you're not a member of ASCE or the Texas section, I invite you to become a member so that you can benefit from being part of this professional association. I am pleased to introduce our presenter for today's training, Langerman Foster. Mr. Foster has practiced geotechnical engineering in the greater Waco area since 1983, when he joined Trinity Engineering Testing Corporation after graduating from the University of Texas, El Paso. Having worked for various geotechnical engineering companies since then, and after 2 years as the executive director of the Texas section of ASCE, he co-founded and works for Langerman Foster Engineering Company in Waco. He was honored to be the chair, he was honored to chair the Texas section ASCE Residential Foundation Oversight Committee, which in 2003 resulted in online publications titled Recommended Practice for the Design of Residential Foundations and Guidelines for the Evaluation and Repair of Residential Foundations. He has presented several papers at Texas section meetings and has enjoyed the lively debates often erupted among Texas geotechnical engineers at those meetings. So if everyone will please listen. Otis, I turn it over to you.
All right. Well, thank you folks that have joined in, and I hope you'll enjoy this. Again, the title, Calculating Expansive Soil Movement from Pressure Swell Tests. This is an expanded version of what was presented at the lightning rounds presentations at the 2017 CCON. So 10 minutes was a pretty short time to try to present this, and hopefully we'll cover a lot of ground in this hour. The purpose: to present a method to estimate expansive soil movement potential, as you can see on the slide there, using the pressure swell tests and using Excel software, an online integration tool, using shrinkage measurements, and comparing results with the TxDOT PVR. And the hope here is that this method will allow engineers to better evaluate more accurately predict expansive soil movements. An overview: this seminar describes a method to convert the restraining pressure in an absorption pressure swell test into an equivalent overburden depth, allowing for an internet-based integration engine to integrate the graph trend line equation and to provide a resulting swell over selected depths. Over selected depth intervals. Brief apologies to those that have not run a lot of, or at least some pressure swell tests, but I think during this presentation maybe it'll become clearer to you what I just read. So here's an outline of what we'll go through. We'll do a brief description of the pressure swell test as we conducted here at Langerman Foster, the resulting graph of those test results, and then using Excel to create an equation for that graph, using an online integrator to determine the swell and geometry to check the integration, and using the PVR method for comparison and further evaluation. We'll then back up a little bit and do a more detailed description of our lab test procedure, do a trial run, present some general comments, and then take audience questions, and then conclude. This might be a little odd, but I want to start off with a disclaimer. As mentioned here, I certainly think what's being presented is correct, but the content has not had the rigorous peer review that probably should occur prior to general use. So all are forewarned, anybody using this is responsible for its validity. I'd like to encourage a close analysis of the embedded equations used in the laboratory form. Those I do intend to make those available to those that are interested. but would encourage everyone to check those. Also, rigorous review by academics and practicing licensed engineers prior to use in general practice is recommended. And there you see that I encourage comments, critical and otherwise, to be sent to me at the email address shown. So here's a very brief description of the lab test procedure. We take a soil sample. It's trimmed from a push tube sample, dried back to less than the plastic limit, placed in a metal ring, loaded to about 250 pounds per square foot vertical confining pressure, inundated and restrained from vertical movement for 24 hours. I should say about 24 hours. The restraining pressure is then reduced by about half, the resulting swell measured after about 24 hours. Pressure is again reduced by half and the resulting swell measured, then reduced to the seating pressure and the resulting swell measured, all these over about 24-hour intervals. Samples then oven dried, and companion testing includes Atterberg limits, minus 200 sieves, moisture content, and unit dry weight determination. So there's a picture of the testing devices. There to your right. I'll pull up something here on the screen for just a second. Here to your right is a picture of a device that's been around for a long time. It's the loading frame, and you see here where I'm pointing the yellow pointer, that's essentially this here. This is the odometer, or the ring. So what you see here is the ring here, the sample sitting in here between a couple of porous stones and filter paper, all inundated in water, and the loading cap here where the pressure is applied, and a dial gauge for measuring the swell that is expected to occur. So this is a quick presentation of the graph that results from this test. What you'll see here is the swell on the y-axis, and you see here on the x-axis the equivalent depth that is equivalent to the pressure that has been converted to a depth. So basically the pressures that are generated are divided by, what we typically do is divide by 120 pounds per square foot to get an equivalent depth. And what this does, you see the 4 points here that are graphed. And you see here the equation that's generated by Excel, and also an R-squared value that shows the correlation of the points to the formula, or rather to the equation. So a brief description of the analysis procedure. You see all that in writing there. And I'm going to go ahead and start walking through that, but for those that will get a copy of the webinar, you'll be able to have that description of the analysis procedure. So here is a display of the lab paper, of all the lab data. So you see the usual information, the boring and the depth that we're at, the description of the material. We show here the pocket pen result, the liquid limit, the plastic limit, the PI, and we also show minus 200, and then the calculated liquidity index. So it shows here the initial moisture content at the start of the test. It shows the moisture content down here at the end of the test. In this area here, you see the different loads that were applied, and you see here the measured swell. Also, at the end of the test, after it has been dried, we also take an average of we measure the diameter in an average of 3 areas, and those are shown here. And we also take an average of 3 heights of the sample as well. And we'll talk a bit more about that a little later on. So what the form does in Excel then is takes these pressures here, and those are, it takes those loads and shows them as the pressures here, and then there's the resulting swell converted to percentage. And here's the equivalent depth where the pressures has been converted to the equivalent depth. So what I've done here is taken and just reversed the order of those columns and brought all that information here. And this then generates the curve that you see. We show the points. Again, you see the percent swell, and you see the equivalent depth, the equation that Excel generated, and the R-squared value. So with that equation that was generated, we then go to an online integrator, and we happen to use this one that seems to do a good job and is fairly straightforward. So the values, that equation is inserted here, and then we conduct the integration from, what I typically do is 2 to 15 feet, and also on the right-hand side I do one from 2 to 20, just depending on what one thinks is probably the appropriate depth of the zone of moisture change. So what you see at the bottom of the integration sheet is it says that's the result of that integration from 2 to 15 feet. A little hard to see, but about 0.53 feet. And here's the number for the integration from 2 to 20 feet. So have taken the numbers here, the 0.53 multiplied by 12 inches, and get about 6.5 inches of swell from the 2 to 15 feet. And from 2 to 20 feet, about 7.5 inches of swell. And just observation, in my calculations, I usually ignore, and in this case have ignored, the first 2 feet. And as most folks know, that those 2 feet can actually contribute considerably to the total swell amount. Then one thing we do as well is to multiply those values, the 6.5 inches, the 7.5 inches, by the 0.67, which is just reducing that by about 1/3 to account for the lateral expansion. So now we'll check by geometry. Basically, the swell should be the area under the curve, which is what that integration function does. So to check and make sure that the integration is giving a realistic result, since doing integration was not necessarily my strong point, and without this integration engine, this kind of approach wouldn't be happening. But since it is doing it, I want to make sure that it's probably realistic in the result, so that it's not just a number being put in a black box and not sure what's done, or that whether the results are accurate. A quick check by geometry can be done. So in this case, we've simplified by just doing a triangle for this area and a rectangle for this area here under the curve from the 2 to 15 feet. And we show the first area here, given the 4.8 inches here, and the second area giving 3.6 inches. And so we're showing by geometry the sum of those two is almost 8.5 inches, and by integration 6.5 inches. And since the 6.5 less than 8.5, that's what we expected. Seems to show that the integration should be correct. Then a comparison. We're going to go, we use a PVR program that we were fortunate enough to get to an engineer, Bob Holloway, who's down in San Antonio. This is a program, of course, that the PVR method's been around a long time, and a lot of different people, I understand, have computerized it, and we've been very comfortable with the one that Bob Holloway produced. So, and it's very straightforward. Here's surcharge pressure, 1 psi. Insert the climatic rating. We insert the plasticity index and how deep that 1 pi applies to in a stratum. In this case, I'm just arbitrarily putting in 1 feet and then the 46. We are assuming this is a full depth of all of the same pi, so to 15 feet. There's a bit of a quirk in the program that it doesn't behave quite right if you just insert data in that first line. For stratum number 1, it seems to require at least 2, so that's the reason you see those. And then we also typically choose a moisture condition of dry so that you get the full range of swell predicted by the PVR method to go from dry to wet. You see the options here, though, of assuming an average moisture content and an optimum moisture. So here's a comparison, 4.5 inches here, 4.5 inches by the swell method or the integration method. So I'm going to back up just a little bit here and revisit the general laboratory procedure. A comment, the basic testing parameters are described in the ASTM method, 4546, method C, and one variation being the loading sequence. Again, we rough trim a sample from a push tube sample for eventual insertion into a metal confining ring. We use rings that measure about 2.5 inches diameter by 1 inch in height. We do moisture content tests on the cuttings to get a field moisture content. We do soil classification tests on the cuttings. We also air dry the rough trim sample to, in an attempt to get to some points lower than the plastic limit. And in our opinion, the plastic limit should equal about that value there, the 0.2 times the liquid limit plus 9, which we understand is McDowell's dry state. And just one thing we do in the lab to kind of reduce the chance that there's an error on the technician's part for that plastic limit value, we found that fat clays generally, the plastic limit comes into about that value. So we have our guys check, and if they're going to be more than plus or minus 2 or plus or minus 3 out of that value, we ask them to redo that test. And then if it comes in same value second time, we stay with that. If it goes closer to that McDowell's dry state value, we'll run with that value. And as a general comment, I think it's interesting that the D698 and 1557 standards or proctors note that the optimum water content is typically a little bit less than the plastic limit. So we then trim the sample after it's been dried back a bit into the ring and again determine a moisture content from those trimmings to get moisture content at test time. We get weights and dimensions needed to determine initial density. We place it in the load frame, load it to about 240 pounds per square foot for seating pressure and inundate it while completely restrained from movement, and then measure the swell pressure after about 24 hours. Again, as stated earlier, remove half the restraining load, measure the swell after about 24 hours, repeat, return to the seating pressure and measure final swell after about 24 hours. So 4 points are generated. We then remove the biscuit in the ring, record the weight, oven dry it, record the weight again. And we also measure the biscuit height and diameter at 3 different locations for each parameter and use the average. And by the way, that can involve a lot of judgment. The measurement here of the dried biscuit is not something that is a rigorous parameter. It's more of an indicator that, for example, if a sample that had a very high PI was tested in a pressure swell test and you didn't get much swell at all or much pressure, and that's of course completely unexpected, then it's very likely that that sample was put in a fairly wet or pre-swelled condition. And so just taking a look at and measuring the dimensions after it's dried back can show that actually there was considerable, what one would expect is you would measure considerable shrinkage, and that would show then, so you wouldn't necessarily be reporting that this sample with a PI of 50 did not have swell. It actually indicates the test might not have been correctly done, and those shrinkage measurements would show that there was considerable shrinkage measured, indicating that it should have also had considerable swell potential. So this state here, I'm going to go to an example to just do an example run of the procedure. So I'm back. And we're going to come here to the Excel. And what you see there is our lab sheet, and it's already been pre-populated with the lab test results, initial moisture content, the final moisture content, the measurements after drying, the loads, the swell that was measured, the pressure that was applied, which is the loads here, converted to the pressure, the swell that was measured, and then the equivalent depth. These have all been generated by the form itself. And you also see, again, you see the numbers of the PI minus 200, the liquidity index, the unit dry weights that are calculated, initial and final, also the void ratios that are calculated for initial and final, and the specific gravity. This form takes and actually calculates specific gravity based on assuming that saturation is 100%, and that's not probably not true, not accurate. That saturation is actually 100, so that specific gravity is probably not accurate either. And of course, 2.8, 2.85, that's pretty high. One would expect a value around 2.7, 2.75. But those calculations there do not influence the measurement, the movement potentials that have been measured. So I've grabbed these results here, the swell and equivalent depth. I've moved them over to here, and now I'm going to grab them, and we're going to a second here. I'm gonna generate a scatter graph of those points. You see that there? I'm going to move those to a new chart, make a new sheet. Just let that be called chart 1. There it is, and because I dislike the portrait layout, I'm gonna change the orientation. I'm sorry, I don't like the landscape layout. Changing the portrait, and we're gonna go ahead and add data points, data labels to the data points. So there's X value, and then, oops, man. And I'm going to add the trend line. So what you see here is what Excel allows you to do. It just threw in a linear line, but allows you to choose from any of these options here. And it also lets you display the equation on the chart. You saw that show up, and the R² value. So now I'm going to just kind of click through here and see which one visually fits the most and also has the best R² value. So there's an exponential trend line, R² 0.98. That's pretty good. Linear R squared 0.86, not so good. Logarithmic, and boy, that looks great visually, and the R squared is more than 0.99. So that's probably going to be the value. And by the way, it typically is for this test. There's the polynomial, visually not so good, and a lower R squared value, and a power, and even lower R squared value. So we'll go back here to the logarithmic, and there's our equation, negative 0.034, and if you can hold just a second, can you, if you can wait just a minute here, I'm gonna can you just grab that and display that there to the left? It'll, yeah. Okay. Okay, we're displaying the formula there. I'm going to back out of this one. And now going to the online integrator. And there's the formula. Okay, we'll get this here in just a second. So there's a formula, and that is a negative 0.034 ln x plus 0.1208. And I'm also going to integrate here from 2 to 15 and go ahead and hit go. And there you see the result. So we get the here in this part right here. Here's the result of that integration, 0.678 feet. By the way, there's a whole lot of decimals there, but I don't think a prediction of soil movement potential is probably any more accurate than about the nearest half inch. So there's 0.68 feet. So I'm going to jump out from here and back to the webinar. Okay, we've looked at that. We've gone to here. We have we had the 0.68 feet. And we're also, here's a slide showing just checking by geometry for those values. And here again is the triangular check. And here we have the 6.81 inches, or actually backing up to 0.56. And here we have, to add all these together, we have the 0.57 and the 0.35 here. We get a 0.92, and that exceeds the 8.16 or the 0.68 here that was calculated by integration. So feeling good about that value. So here we're checking that again by the PVR method, and we had about the 8 inches or so with the 2 to 15 feet, and then times the reduction factor gives us about 5.5 inches, and the PVR result from dry to wet 4.2 inches, or about 4 inches. So these are pretty close values. So some general comments. We've, of course, assumed similar PI and granular content to full depth. So if you've got varying strata, they should be analyzed individually. The method ignores in situ water content to predict the swell, so it's intended to give an idea of potential movement from dry to wet conditions. Integrating from 2 to 15 feet ignores the upper 2 feet. And those 2 feet likely have the highest potential vertical movement, as I mentioned earlier. And just to confess, I don't have a good reason for starting the integral at 2, except that when I first started using the method, I just chose that boundary condition. Deciding on an appropriate boundary condition would be an interesting discussion. And also, this integration method allows you to account for removal and replacement that's intended to reduce the potential vertical movement. If 5 feet is removed and replaced, and the zone being considered is previously was from 2 to 15, the upper integral limit would just change from 2 to the 5. So you would integrate from 5 to 15 feet. The examples shown assume one sample represents the full depth of potential vertical movement, implying essentially the same PI and granular content within the depth of interest. Even if those values of PI and -200 are essentially the same, the full depth, I think it'd be more appropriate to conduct tests on samples from, say, 0 to 5 feet, 5 to 10, and 10 to 15, and maybe deeper if appropriate. But however, I do think that even with just the one sample, it still, I think, gives a good idea of the movement potential within that whole zone of those similar characteristics because of drying it back to drier than the plastic limit. Note as to that lab form, the one we'll eventually have available from this webinar, we intend to update it so that it shows the field moisture content and the calculated void heights for the initial and final unit weights. And then a comment again about that specific gravity calculation being based on assuming 100% saturation, which again is likely not correct. But for purposes of this presentation, the specific gravity and void ratio values don't impact the movement estimates we're discussing. So swell testing is one of the methods for predicting expansive soil movement in the Texas section. ASCE's recommended practice for the design of residential foundations. There you see a link to those publications. Those are to that publication. It's available for free. So the methods that are shown is the TxDOT PVR method, swell tests, suction and hydrometer tests, linear shrinkage tests, and any other method which can be documented and defended as good engineering practice in accordance with the principles of unsaturated soil mechanics. I do want to note, though, that the method of analyzing swell tests is presented in this webinar to predict movement potential was not known when the guidelines were produced. And of course, there are other methods out there, and I'd like to note in particular the shrink test water content method that Dr. Brio and others at Texas A&M have presented. Also recently became aware of the centrifuge technology method by Zornberg and Armstrong, UT Austin. And there's some empirical methods, just looking at Atterberg limit test results and other correlations with soil properties to predict potential soil movement. And I think the book Correlations of Soil Properties by Carter and Bentley, some of you may have copies of that. It has a brief little section on expansive soils and a few different empirical methods to predict the movements. And a comment here, I'd like to suggest that the ASCE Texas section consider adding the shrink test water content method and maybe centrifuge technology methods and maybe other methods being used in Texas that meet the criteria stated in the previous item, in item 5 of what the ASCE guidelines were listing. And so those that meet that criteria and that might be proposed and currently used by reputable practitioners. I do prefer the terminology of potential vertical movement over potential vertical rise, since soils can rise and shrink. And a comment that when I first began in engineering practice in the early 1980s, the pressure swell test method that I was taught was pretty much as we presented, where we have full restraint initially, an inundation followed by incremental reduction of that restraint. And I understand that other labs use this procedure and have used it for a long time. The ASTM standard, as I've read it, doesn't seem to describe this procedure. And if others read the standard the same way and it's commonly used, I think I'd like to see ASTM consider including it within the standard so that we can all be doing it in the same way. A comment on just lab personnel. I'd suggest using the experienced lab personnel who care about quality and can dry the sample to a few points dry of the plastic limit with minimal cracking. It requires some judgment and care for quality on the part of the lab person running the test. Additional comments. As I mentioned earlier, soil movement estimates are approximate, and I'd suggest in the way our industry reports them for clients anyway, in the world of actual construction, that rounding to the nearest half inch is suggested. Many of you know Phil King out of San Antonio. He and others conducted numerous swell tests when practicing in the San Antonio area, and they took some of the swell tests and went ahead and let them continue to swell over several months. And he said many of them had secondary swell of about twice the primary swell. And so that can be pretty disconcerting if and difficult for the lab consulting labs to actually have tests that ran months before we could give results. But worth some thought, in my opinion. And then a paper from the Texas section 2001 spring meeting proceedings by the Texas section titled Under Slab In Situ Moisture Content, and again referencing Philip King and Struzik, Laura, and Stephen. They discuss or present what I think is a very useful and practical study of the relationship between the plastic limit, the moisture content, the liquidity index, and the state of swell, and that just some reference to that paper can help refine some specific potential vertical movement predictions if one wanted to consider the infield moisture conditions at the time of the sampling. That paper contains a graph that would indicate that the pressure swell tests with initial water content below the plastic limit, like we're advising be done and we do in our procedure, that it really should indicate more swell than would be predicted by the TxDOT PVR method, because as you saw in the program for the PVR method, it assumes an initial dry state of about the plastic limit. And I personally would like to see studies comparing the height of the void, which comes from the void ratio E, where E is equal to the volume of void divided by the volume of solid, which is also the height of the void divided by the height of the solids at the start and at the end of pressure swell tests, and just to see how the difference between them compares to the swell test result and to predictions of soil movement potential. And I wanted to just remind folks of the potential for rebound as a contributor to movement potential. and how in an excavation that fat clays that have been excavated may expand simply from overburden removal. And that needs to be considered when estimating movement potential. So one might ask, how do you resolve a big difference between the pressure swell results and the PVR method? I guess my response would be mostly judgment and experience, and preferably local experience. It can be disconcerting, certainly, if one runs PVR calculations and swell tests, and the swell tests are twice those values. It requires some thought. And how do predictions from this method compare with field measurements? Well, I don't know, and we hope someone will have the resources and desire to conduct such comparisons. With just a few minutes here, I'm gonna jump out for just a second. I want to go ahead and show the graph that was in the paper by Phil King and others. I again thought this was very useful, but here are some lines taken from that paper. And down here, this quote, the soil is probably in a non-swelled state if its liquidity index is negative or close to negative 0.2, and it is likely in a fully swelled condition if its liquidity index is on the order of plus 0.3. So here they show water content on the y-axis, and here's the value showing about 100% swell when you're getting near the swell limit. And of course, it's swell limit at 100% and no swell at the shrinkage limit. And so here they have graphed a plastic limit, and the way they've indicated here is that if a sample is at its plastic limit, then it's probably 33% of the way into its swelling potential. So say one were to predict that you were going to get 5 or 6 inches of movement, then 2 inches of that movement has probably already occurred if the existing moisture content is around the plastic limit. So when we're running the pressure swell tests and starting them at a lower value than the plastic limit, they're going to show more movement potential than the PVR method might be, which starts at about the plastic limit. And then here's a graph of liquidity index versus depth, and the utility of that kind of graph can show that based on Phil King's and others' work here, if we're showing negative values here, that it's in an unswelled state, so it has most of its swelling potential left. And here's some points graphed to that side of the line, and this just taken from one project, with a couple of the points showing that it is on the positive side of the liquidity index, meaning that it is in a somewhat swelled or a little bit of a pre-swelled state. And with that, I'd like to conclude with the intent here, or what was done, is this seminar described a method to predict potential vertical movement using the pressure swell tests. And I want to thank you for all those that have listened in. Again, I would very much appreciate your feedback, and there are ways that you can reach me as shown there. And also, I believe a copy of the PowerPoint will be available in the laboratory data sheet, probably from the Texas section, and I did not put in their phone numbers here. They are not trying to keep those secret. I just left those off. So, but I think most on here know how to get those numbers, and there's also the website for Texas ASCE. I also want to mention the geotech organizations in Texas. There's the Texas Geo Institute. There you see who's the current president. He's He's the one who will be leaving here soon, but he's available for questions, and there's his email address. There's also in the San Antonio Geo Institute, records I looked at showed Phil King as current president, and there's his contact information. And the Houston Geo Institute, Rebecca Cummins with Terracon is the president there. There's her contact information. It's also the Dallas Branch Geo Institute, and I was not able to get who the current president is for that or contact information. And then there's numerous student chapter and the student chapter Geo Institutes that are at several of the Texas universities. And with that, would like to open it up to audience questions.
Thank you, Otis. If anyone has a question, go ahead and type it into the chat area so that we can get it and see it. Let's see, do have one. You mentioned that you want minimal cracking when you are drying your sample. Any other conditions required for sample quality?
Good question, and I think that the sample needs to, as much as possible, be a very intact sample, and probably samples that are obviously too wet should be avoided, in my opinion. I think if a test is run on a sample that is moist or above the plastic limit, obviously above the plastic limit, or also often the pocket pentrometers, a lower pocket pen indicating a lower strength, which indicates a less dry sample, that those, in my opinion, would just give a misleading result and might indicate to a layman or to those who have less experience in tests with fat clays that they might think that this fat clay with a high PI actually had little swelling potential. And that was true at that moisture content, but probably not true for the time of construction, when it's very possible that that soil zone might have dried back considerably. Hope that answered somewhat.
All right. Let's see. Mike, do you have any other questions?
Yeah, it looks like we've got a few coming through in the questions box. We got a few more minutes here. Otis, what is the rationale for reducing the swell test result for lateral restraint?
Because it's placed in a steel ring, the ring is not allowing for any kind of lateral movement in the test, so it's all forced upward. And in the field, those clays are going to be allowed to swell laterally as well as upwards. Often there's substantial cracking in the field, so it won't be all in the upward direction, even though the shrink swell test as it's conducted would be showing a value as if it were all going vertical. So choosing an appropriate reduction factor at this time, yeah, I've kind of settled on that 1/3 reduction, but I'd sure like others with experience in this and academics to weigh in with what might be a more appropriate value there for the reduction factor.
Alrighty, thank you. We got a few more questions here. We're not going to have time to get to them all, so if you don't hear your question answered, you'll be receiving a follow-up email in the coming days with an answer. One more here. Someone is wondering if the 24-hour load duration is too short for soils, and they're wondering if you know of any studies that have longer interval durations.
I don't know of studies in particular of longer durations, except for Phil King letting one go for months, and others that were working with him on that. I think that a longer time could be appropriate, and there could be specific cases where if a technician were to note that it goes to check a value at 24 hours and it doesn't seem to have leveled off, but it's still increasing, then it might be appropriate to allow it to continue to increase. But I think from the standpoint of a commercial lab, where there's also some pressures to get lab results out to a client in a timely fashion, and this kind of test takes several days anyway, that the results that are generated from a 24-hour interval are probably close enough to give an indication of the swelling potential to the nearest half inch. And I think too, there can be issues could come about if one were to not be consistent within a single test in terms of the time that it's allowed to swell between the intervals. If one were to allow 48 hours, say, between one interval, you probably would be wise to keep that same interval throughout the test for the different points.
All right, thank you, Otis. And we have time for one last question before we wrap it up here. Somebody is wondering, have you tested the repeatability of your pressure swell test results?
That's a good question. Not a specific case that I can recall. If I get an odd result that just doesn't seem to make sense, I do ask that it be done again. But I don't recall a specific incidence of that occurring. But I think it is wise that if an engineer gets results that just don't seem to be appropriate, that the tests be done again. And from a sample, at least one hopes that there would be samples available, that enough borings were done that one could get a sample near the same depth and within the same strata that was that generated an odd test result.
All right, well, that's all the time we have for questions today. Thank you very much for answering those, Otis. I think Russell has a few closing remarks, and then we'll get you all back to work.
All right. Thank you again for participating in today's ASCE Texas Section webinar. As mentioned before, individual registrants should receive an attendance acknowledgement without